Welcome friends, Igor is here, and in this video we will prove that the span construction results in a subspace. In this lesson, we will expand the notions of linear combinations and spans from column vectors to arbitrary vector spaces, prove that a span of a set of vectors in any vector space is always a subspace of this space, and justify the terminology of the column space and row space of a matrix by proving that they are indeed vector spaces. Let's get started. We defined the notions of linear combinations and spans in the context of column vectors, but these notions were based on the ability to scalar multiply vectors and add vectors. These two operations exist in every vector space. Therefore, the notion of linear combination makes sense in the context of an arbitrary vector space. Let's work out an example of a linear combination in the vector space of 2 by 3 matrices. We take 3 vectors in this vector space. In this case, they are 2 by 3 matrices, and let's construct a linear combination of these 3 vectors. For example, 4x minus 2y plus 3z. To compute the result of this linear combination, we simply need to use the definitions of the operations in this vector space. First of all, we know how to multiply matrices by scalars. Also, we know how to add matrices. This results in a vector in our vector space, and this vector is the linear combination of the given 3 vectors with the prescribed 3 scalars. Now that we know how to form and compute linear combinations in an arbitrary vector space, we can define the notion of a span of a set of vectors. Suppose we have a vector space V, and we take a set of vectors in this vector space. Then their span is the set of all possible linear combinations of these vectors. The vectors are fixed, but the scalars are allowed to take any possible values. Let's prove that the span of any set of vectors in a vector space is automatically a subspace of this vector space. In the previous video, we discovered a simple 3-step test for a subspace, so I'm going to apply this test here. Step number 1, we need to make sure that our subset is not empty. For example, we can create an explicit linear combination when all the scalars are equal to 0. We know that in any vector space, a scalar multiple of a vector by 0 scalar is the 0 vector, and in particular, this computation shows that 0 vector is always a member of a span, no matter which set S you take to construct the span. We have found at least one vector in the span, therefore the span is not the empty set. Second step, we need to check that this subset is closed under vector addition. We take 2 arbitrary vectors in the span of S, and we need to prove that their sum, x plus y, is also an element of the same set, the span of S. To be in the span of the set S means to be a linear combination of vectors in S. Therefore, the vector x is a linear combination of vectors in S. Let's say we use alpha scalars for this combination, and the vector y is a linear combination of vectors in S. Let's say we use scalars betas to construct this linear combination. Let's add these two equations to each other, and on the right-hand side, we are going to use some properties of vector spaces. First of all, addition of vectors is commutative, and therefore we can rearrange the terms. Also, we are free to use parentheses in any way we like, because the addition of vectors is associative. Within each of the parentheses, we are going to use the distributive property, and our expression simplifies as follows. But now you see, this computation says that the vector x plus y is a linear combination of the vectors in S, therefore it is indeed a vector in the span of S. Step 3, we need to prove that the span of S is closed under scalar multiplication. We are going to take an arbitrary vector x from the span and an arbitrary scalar alpha. Our goal is to prove that a scalar multiple of the vector x by the scalar alpha is a member of the span of S. The assumption that the vector x comes from the span of S means x can be expressed as a linear combination of the vectors in S. Let's scale both sides of this equation by the scalar alpha, and on the right-hand side, we are going to apply the distributive property of vector spaces. Then we recall the associative property for scalar multiplication, and this computation shows that the scalar multiple of the vector x by the scalar alpha is a linear combination of the vectors from S. Therefore, this vector is in the span. We completed the three-step check for a subspace, and therefore we proved that the span of any set of vectors is a subspace of a vector space. An immediate application of this general observation is that the column space of a matrix is a subspace of the vector space of column vectors. This is an automatic consequence of the fact that spans are always subspaces, because we defined the column space of a matrix as a span of the set of its column vectors. Similarly, the row space of a matrix is also a subspace of the column vectors. And this is because the row space of a matrix A is the column space of the matrix A transpose, and we already discovered that the column space of any matrix is a subspace. If you found this video useful, please give it a like to help others discover this content, and subscribe to this channel to see more of these videos. In the next video in this series, we will generalize the notions of linear dependence and linear independence from column vectors to arbitrary vector spaces. I will see you later.